Good afternoon, everyone. I would like to welcome you again after a break. And I would like to also introduce Mr. Nikita Tarakanov, who will talk about exploiting hardcore pool corruption in Microsoft Windows kernel. And I would like also to say, if you get any questions, suggestions, or something like this, just raise your hand and I will go with a microphone because we would like to have a clear voice on the tape. Okay, the floor is yours.
Okay. So what's up, everyone? I'm Nikita Tarakanov. I like trolling. So I'm an independent security researcher from Russia. I have several aliases: vulnerability assassin. People call me crazy wild Russian. Also, I have alias aligner of stars. Probably heard funny story with semantic. Next one, it's Cyrillic. It's related to some Twitter battle with some IT security veteran in Russia, but the only thing you have to know about me is that I'm not just a nice dude. So I will talk about some kernel pool basics, about previous research that was done by several researchers, about new approach, and conclusion and question and answers. So why kernel? Why pool overflows? There are sandboxes in modern applications like Google Chrome, Internet Explorer, Adobe Reader, and I think it's a cool thing to attack kernel and escape sandbox. And a great example of that, it's latest pawn of Google Chrome by Niels and John from MWR Labs. So they basically, first step, it was gaining execution and sandbox process using type confusion vulnerability in WebKit, and next they attack kernel using pool overflow in Win32k.sys. I work in this industry since 2008, and I analyze almost every security fix by Microsoft, especially for kernel. And most of the vulnerabilities are memory corruptions, and most of the memory corruptions are pool overflows. So started from Windows 7, Microsoft enhances security of pool allocator. And in Windows 8, it's very secured. So let's talk about previous research. Following slides, it's just copy and paste from previous research. And personally, I suggest you to read awesome slides, awesome work by Tarjei Mandt. In my opinion, it's most comprehensive work. Also, the great work by Eric was done on advanced manipulation of pool and also heap and userland on Windows 8. So let's kick it. If we talk about heap, I mean dynamic memory, there is one difference between userland and kernel land, that pool divides in several types. There is a non-paged memory, paged memory, session memory, and pool is defined by a structure pool descriptor. The initial descriptors for page and non-page pools are defined in a pool vector array. So this is how it looks like. There are a lot of fields, but the most interesting are ListHeads and pen and freeze. So ListHeads is just an array of lists and of single list of chunks. Because granularity is 8 bytes, and ListHeads contain the last entry is 4080 bytes. So pool header, like header in userland, defines a chunk. And it contains several fields like previous size, block size, pool index, pool type, pool tag. For example, previous size is size of previous chunk, block size is size of chunk, pool type it's type of actually memory, non-page, page, session. And if we talk about differences of bits, actually they look same, but on 64 bits there is a pointer to eProcess. The main thing that if we talk about free pool chunks, after pool headers there's a list entry structure, and it contains pointers to forward and backward headers. So this is how it looks in graphic way. So there is a header. There is a header and pointers to forward and backwards. So, you know, Pool Allocator was developed to make allocations faster. So for different sizes, it uses different lists. And for small chunks, it's used Lookaside Lists. This list is defined in the process control block. And the maximum block size of that uses in this list is 260 and 56 bytes. So this is how it looks like in graphic way. Okay. If we talk about large allocations that exceeds page boundaries, there is a special function, exp allocate big pool, and actually there are special list for allocations of page count 1, 2, and 3. So basically, when you allocate some memory, first of all, it search Lookaside lists and ListHeads, and then pool page allocator. If we talk about interfaces, there are a lot of functions that you can use to allocate memory in kernel, but the main function is xallocate pool with stack. And if we talk about order, how to allocator allocates memory, first of all, it allocates chunk in the front, on the bottom of the page, and next from the bottom. And one of the key points that previous size of first chunk is 0. Basically, it means that behind that chunk there is no chunk because it's first on the page. So, talking about free algorithm, also like for allocation, there are a lot of functions to free memory, but the main function is xFree pool with stack. Also for reducing fragmentation, if there are chunks that are also free adjacent, allocator merges these chunks. So, for example, if we have such situation, this chunk is free, this also free, and there is a busy chunk. When you free this chunk, allocator first of all merges to previous and next to to following and to previous. So in the end, you'll get one big free chunk. So talking about previous research on in this domain, first talk was in 2005, but in my opinion, talk research by Costa was cool because he revealed some internals of pool allocator, and next Tarjei has done a real great job, and in the end Eric also revealed some cool stuff for Windows 8. So research by Costa, it was in 2008, and so before Windows 7 release, and almost every technique that he revealed end up so-called write-for primitive. For example, you have such situation. There is a double linked list, and you have two entries, and you remove entry, and it leads to primitive write4 if or write8 when you control address and value. So arbitrary memory override. And one of the technique is to, for example, there is a header, you allocate memory, there is overflow, and you overflow header of next chunk. You overflow previous size of next header, and you full allocator that he thinks that behind that header there is a fake header. And when you free this header, you get this primitive. So you control data and you control address, and it leads to pawn of the system. Next, in Windows 7, almost every technique by Costa were killed, and Tarjei discovered a lot of interesting stuff. There are 5 techniques, but I'm not gonna talk about them. It's better to see original slides. And Microsoft did a really great job on Windows 8 and eliminated almost every technique that Tarjei discovered. And Tarjei continued his work on Win 8 and discovered 2 techniques. So actually, split chunk and block size, they are kind of same. So I'm gonna talk about BlockSize attack. So when you free some chunk, it's put in free list or Lookaside, depending on block size. So when you overflow, you can override block size, and you can full allocator to put it different arbitrary free list. And the key point of this technique I can show you in a graphic way. So, for example, you have such situation. There is a page, and there is 4 chunks. And from this chunk, you overflow these 2 chunks. So you overwrite block size of this chunk, next freezes block, because you overwrite block size of this chunk to fill the rest of the page. So pool allocator thinks that there should be one big chunk that covers the end of the page. Next, you allocate with something controllable like Unicode string and fills it memory. So basically, it leads to corruption of data of this chunk. So but talking about prerequisites and ideas of previous research, all research is focused on pool allocator, metadata mechanisms. You have to know how to control pool. You have to control overflowing data. There are a lot of prerequisites, and you know, some vulnerabilities are not exploitable using these techniques. So the problem is, what if there are vulnerabilities that you can easily exploit, and there are another. So I separate pool overflows into two groups. Some of the suite that can be easily exploited, and some of them are hardcore. So, for example, hardcore vulnerabilities. If you have vulnerability like mem set with zeros, there is no technique to exploit such overflow, or like this one, or even with uncontrolled memory. And you know, I was thinking why researchers, you know, are focused on pool allocator. Why they, you know, struggling with metadata, with mechanisms. I was imagining what if in Windows 9, for example, pool allocator becomes totally bulletproof. So there is no technique against attacking metadata mechanisms. So what leaves? And I think, what about attacking data? So I discovered that this direct kernel object header manipulation thing, you know, when operating system works, it uses objects. Objects have headers. Object header defines object. So basically, you know, direct kernel object manipulation is well known in the rootkit world, and I was curious why it's not used in the exploitation world. And I thought, I have to see what's there. So take a look at object header. There is some interesting field, object type, and its pointer. And after some fields, there is actually body, so actually object. It's from Windows Research Kit. It's Windows 2003 SP0. And since Vista, object header changed a little bit. There is no pointer. There is an index. Actually, it's index to array of object type elements. Also, object type has interesting field, object type initializers. And well, there is no change between XP 2003 and Windows 8. And this field contains interesting things. It contains pointers to functions or procedures. For example, dump procedure, open, parse procedure, and so on. So there's an example of object type initializers of LPC object. So there's, for example, open procedure is LPC open port. For close procedure, it's LPCC close port, and so on. So talking about array of object types, there is an interesting thing that actual elements starts from the third one. There is a pointers to actual object types, and first item and second type are special. First time is 0, and second time is bad above all. On a 64-bit operating system, it looks quite the same, except that bad bobo is extended by zeros. So the idea is smash object header, next invoke some special system call. This system call triggers the reference of smashed pointer, and basically it leads to hijack of control flow. So the steps are quite easy. First of all, we spray pool with objects. Next, we fragment pool to predict where allocation is going to take place. And the key point is to make hole at the bottom of the page, because when you overflow data and you overflow header on the next page, you will not trigger any checks or blue screen, Because as I showed, first chunk on the page has a previous size equals 0. So basically, there's no chunk behind. Next, you trigger overflow. So smash object header, call special system call, and gain execution control with kernel privilege. Basically, because there are a lot of procedures, there are a lot of system calls to invoke them, but my choice is this one, basically because it gives you control of execution flow, and it contains security in the name. So, for example, when you smash object header, you control type index value. Next, it gets element of object type, and next there is a dereference, and here you gain control of EIP or RIP. So there are several ideas in this technique. First one is using out-of-bounds access of this array. Next is a special entry, which is bad bobo. And next one is object type confusion, or aka direct kernel object manipulation. So if you take a look at this array, it starts, as I said, from third. And actually, because type index is a byte, so there are 256 elements, but there are not a lot of object types, so it initialized with zeros. So basically, the cool thing that the only prerequisite just on 1 byte of overflown data. So, for example, if you overflow with zeros, you trigger null pointer reference. But the awful thing that you can't allocate memory at null page on Windows 8, and after security fix, which is MF 13031, you can't allocate memory at null page on 64-bit operating system. But on the other hand, you can allocate on 32 bits, so it works. And the funny thing that I gave talk at Hack in the Box in April, and before the security fix release, it works quite well, except Windows 8. But Microsoft, this security fix fixed 2 race conditions that were discovered by Matthijs Jurczyk and Ginwell Colland, and also killed the null pointer dereference on 64-bit operating system. So yeah, this animated pictures, shows my feelings on that morning. Okay. Second idea is to use this magic constant. Actually, I'm curious because Matthijs Jurczyk won a Pony Award for some interesting vulnerability, and if I've got this magic entry, bad bobo, Matthijs Jurczyk has another magic constant, bad DOOO. So I think some programmist from Microsoft likes constant that starts with bad something, or maybe it's CIA backdoor, I don't know. So basically, you have to allocate at this address fake entry and gain execution. But the funny thing that using this technique, and this technique, 64-bit operating system are more vulnerable, because bad bobo is in a user space address, is the address of user space. But on 32-bit, it's in kernel land. So, but on the other hand, if Microsoft will implement SMAP, it will eliminate this technique. This is just output from debugger. So as you can see, it's in the userland, and on 32 bits, you have to spray page pool. Talking about object type confusion, different objects have different functions. For example, most of the objects have query security procedure is C default object method. But some, for example, registry, it's a CMP security method, and file is IOP get security object. So the idea is to change type of object and redirect execution flow with fake data to function. For example, to functions that think that it process data of registry object, but actually it's not registry object. But the drawback of this technique that kernel object in Windows operating system are complex structures, and you have to have precise control over overflowing data, because there is pointers, and for example, if you overflow with some zeros, you will trigger null pointer dereference, blue screen of death, and game over. So when I release first time after hacking the box, I got some feedback from, in my opinion, old school elite from JR Security. Actually, Brett Spender is a maintainer of JR Security behind that account, and he tweeted that it's funny because that people that develop exploits for Windows just now figure out that there are useful magic values to corrupt JSON objects and blah, blah, blah. And I started to chat with him, and it ended in my opinion, in this messages from him. So he tweeted that, yeah, the point is it doesn't pay to willfully ignorant about research just because it's not for Linux, just for Windows. But the thing is that there are far more familiarities and differences in security lessons to be learned and methods to fix them. So basically, yes, a theory of hijack of execution flow is known for years, but implementations are not. So this implementation is not so well known. So in conclusion, nowadays, and personally I claim that generic techniques are dead, that nowadays there are only application-specific techniques, but this technique is kind of generic. Next thing that Microsoft started to enhance security of pool allocator from Windows 7. Enhance in Windows 8, maybe will enhance in Windows 8.1, but totally forgot about security of object manager. And there is no such thing like security cookie object header. So I think that Microsoft should implement cookie object header to kill this technique. And if Microsoft implements SMAP in Windows 8.1 or maybe 9, it will eliminate one idea using BedBovo on a 64-bit operating system. But personally, I think that it's not gonna change a lot. I think that we'll be powering Windows kernel pool corruptions forever. So that's it. Any questions?